Hi, my name is Ulysses Lin, and I'll be talking about Google File System. Today, Google Cloud and Google products such as YouTube, Drive, and Gmail rely on Google's massive storage system called Colossus. I'll be talking about a predecessor of Colossus called Google File System, or GFS, which is the topic of the 2003 paper called the Google File System by Gamawat, Gobioff, and Leong, and referred to in the Raft paper. GFS is a distributed file system that has a typical file system interface. Clients can overwrite parts of files or do something called record append, which is adding to a file without overwriting. And you can do something called snapshot, which is just copying a file or directory at a low cost. For main aspects within the Google context, I want to say that as a note, the authors at the time thought that these were a radical departure from the traditional storage systems, but some of these sound a lot like what we should be expecting of distributed systems as outlined in this class. One, failure should be expected. Two, typically GFS stores huge archival or repository files. They could be gigabytes in size. And because the files are so large, in very few cases will a client be overwriting, but rather just appending. So this is this concept of once written, read only. There's a lot of one-time scanning for a huge block of data. So caching loses its appeal. And finally, flexibility. You want to relax the consistency model to avoid burdening applications. GFS has a way to atomically accommodate multiple clients appending data concurrently. The authors also follow up with some of these assumptions shown here. Most of these are somewhat repetitive, so I'm just going to call out number 6, which emphasizes that high bandwidth is more important than low latency because clients typically seek huge files over little snippets of data. Let's get into the main players within a cluster in the system. We have a master that serves as a coordinator, chunk servers, which handle data, and you have chunks of data. Masters store metadata in memory, maintain logs, and communicate chunk data management information with chunk servers. And they provide clients with the metadata, and clients subsequently work directly with the chunk servers for reads or writes. Masters are meant to be very lightweight, storing just 64 bytes of metadata for every 64 megabytes of chunk data. Chunk servers store the chunks on local disks. They run checksums to validate data integrity before returning data and store chunk version numbers as metadata. And there's chunks of data, ID'd by chunk handles, accessed by the client via chunk servers. Masters and chunks are duplicated as replicas at a default of 3 times for fault tolerance. Now let's look into some typical interactions among these. A client sends a file name and a chunk index or location within a file for access. The master then sends back to the client a chunk handle and replica locations. The client then caches this metadata, not the data itself, just the metadata, and sends a request to the closest replica. The master oversees chunk replication, prioritizing chunks with low counts of replication or things needed for client progress or load balancing. So for deletion of files, the master removes them from the metadata. Then chunk servers send heartbeat messages with the data replying with updated metadata, and the chunk server will then delete the data. Let's say there are multiple clients and they open a long TCP connection and concurrently write to a chunk by writing to all of its replicas. The snippets are added atomically, and it's okay with Google File System if the replicas don't look exactly like each other, at times due to some initial ordering differences or failures. What happens is the master grants a chunk lease to a primary chunk server, which tracks the correct ordering of the data added. The primary chunk server then sends a write request of the correct ordering to its secondary replicas. If there's a failure, the write isn't reported, but retried several times. As for problems, a log of operations is maintained by the master So every time a new chunk server or replica is made, the log is updated and replicated. Masters have replicas in case of crashes, and masters can restart almost instantly despite long logs because checkpoints are actually saved, and a master could just restart from one of those. As for stale chunks, whenever a master grants a lease, it updates the chunk version so that stale chunks aren't mutated or reported to the client. If a whole bunch of clients are accessing one chunk at the same time, then the solution is to make many replicas, stagger application start times, and have clients read from other clients. The authors ran tests on 2 sample clusters, A and B, with A seeing less consistent accessing of chunks, typically in small snippets. They found that writes took much longer than reads, as you have to write to all the replicas while reading is just from one. Masters also recover from failure quickly, as they're just 50 to 100 megabytes of metadata, and chunk servers are very fast as they are pipelined. They send data to the closest chunk server. Google File System is the simple and flexible, with file system control via master and data transfer between client and chunk servers, so the master doesn't become bottlenecked. Thank you for your time.